Hello, in this video we're going to discuss properties of group homomorphisms. Alright, so here we discuss some properties of a group homomorphisms. First, given a group homomorphism from a group G to a group H, phi of E is the identity of H. Second, for every group element, the inverse of phi of G is phi of G inverse. More generally, this one's not in the book, but it's also true. For any integer n, phi of the nth power of G is the nth power of phi of G. The third property is that for any subgroup of G, its image is also a subgroup of H. And for any subgroup of the codomain H, the pre-image is a subgroup of G. Moreover, if K is normal in the codomain, then the pre-image is normal in the domain. Notice, of course, so this is the symbol I use for normal subgroup. If you need a reminder, the definition of image of a subset is given by applying your function to each element in that subset. So it's the set of all y coordinates for the set for each x coordinate in this set you're taking the image of. Likewise, the pre-image, given a set of y coordinates, the pre-image is the set of all x coordinates such that the function maps that x to that y. So it's all x in the domain, such that phi of x is in that subset in the codomain. So if you go back to my video on isomorphisms, video series on isomorphisms, you will see I proved property 1 in the context of group isomorphisms, and you'll discover that nothing about that proof used the fact that phi was surjective and injective. It only used the fact that phi preserved multiplication. So that proof actually holds for group homomorphisms as well. The same thing was true for properties 2 and 2 prime. They only used the multiplication property. So those proofs are still the same for group homomorphisms. So those two results are true. So I'm only going to focus on these latter two facts for this video. So let's prove the third claim. Let K be a subgroup of G. We want to prove that phi of K, the image of K, is a subgroup of H. We're going to use the subgroup criterion, which means given two elements in the image, we want to show x, y inverse is also in the image. So here's the proof. Let's take x and y in the image. Well, what does that mean? That means there exists two elements, A and B, in the set K, such that phi of A equals x and phi of B equals y. These are homomorphisms, so there could be more than one possible value for A and more than one possible value for B. We know there just exists at least one, because x and y are in the image. Well, let's calculate x, y inverse. By substitution, x is equal to phi of A. By substitution, y is equal to phi of B. The inverse of phi of B is equal to phi of B inverse by a property of group homomorphisms. And since phi is a group homomorphism, phi of A times phi of B inverse is equal to phi of A times B inverse. So what we've managed to show is that this product is actually the image of some element of G. So at the very least, we managed to show that this is in the image of G. But we need to show it's in the image of K. So how do we do that? Well, one of the hypotheses we haven't used yet is that K is a subgroup. A and B were elements in K. So since K is a subgroup, it follows that AB inverse is an element of K. So now we see that XY inverse is equal to phi of an element in K. So XY inverse is itself in the image of K. So we took two elements in the image. We showed that XY inverse is in the image. By the subgroup criterion, we conclude that the image is a subgroup. All right, let's prove this claim. So let K be a subgroup of H. We want to prove that the preimage of K is a subgroup of G. Let's try doing it using the subgroup criterion, which means that given two elements in the preimage, X and Y, we want to show X, Y inverse is also in the preimage. So let X and Y be in the preimage. What does that mean? That means phi of X and phi of Y are both elements in K. Well, since K is a subgroup of H, then phi of X times phi of Y inverse is an element in H. Well, then by properties of group homomorphisms, phi of X times phi of Y inverse is equal to phi of X times phi of Y inverse is equal to phi of the product XY inverse. Since these three things are all equal and the first product was an element in H, this last calculation formula is also an element in H. And then that implies that X times Y inverse is in fact in the preimage. So by the subgroup criterion, we do have that the preimage is a subgroup of G. Now let's suppose that K is a normal subgroup in H. So this is the codomain. We want to prove that the preimage is a normal subgroup in G. So the approach I'm going to take for this proof is to prove that for any element in G and any element X in the preimage, G inverse XG is also in the preimage. So the preimage is closed under conjugation. Note that this is true if and only if phi of G inverse XG is in K, because that's the definition of preimage. So that's the calculation we're going to show. Well, let's look at phi of G inverse XG. This is a group homomorphism, so that's equal to so phi of the product is the product of the phis. Phi of G inverse is the inverse of phi of G. And so you get this expression. We know phi of X in the middle here is an element in K, and we know K is normal in H. And the two outside terms are elements in H now, because they're phi of G. So we're conjugating an element in K by one element in H. And therefore, this product is an element in K, because K is normal in H. And again, since these two things are equal, that means phi of G inverse XG is also an element in K. Whence that implies that G inverse XG is an element in the preimage. Which means that conjugating elements in the preimage by elements in G give you elements in the preimage. Therefore, the preimage of K is in fact normal in G.